Welcome to our soil testing video series, jointly presented by the Geotechnical Division of the HKIE and the Geotechnical Engineering Office of the CEDD. The production of this series is made possible by the generous support of our sponsors. In this video, we're going to explore an important aspect of soil testing, particle size distribution, or PSD in short. Before we jump into the specifics, I reckon many of you have seen the terms gravel, sand, silt, and clay from the ground investigation and laboratory testing reports. But let's address a common misconception first. When we talk about these terms in those reports, it's important to note that they refer to grain size and are not directly related to the soil's geological origin. Anything from 2 mm to 60 mm is classified as gravel, from 60 microns to 2 mm as sand, from 2 microns to 60 microns as silt, and anything smaller than 2 microns is classified as clay. Particle size distribution tells us about the distribution and proportion of different particle sizes in a soil sample. Under GeoSpec 3, the PSD curve should provide the percentage by mass of different grain sizes in a soil. The PSD curves of a few soils are shown in this chart. In particular, a typical PSD curve for a poorly graded uniform sand and another PSD curve for a well-graded, completely decomposed granite are illustrated. You can see how different the PSD curves of these soils are. What are the test methods for particle size distribution? First of all, we need to consider whether it's the coarse portion or fine portion of the soil sample. For the coarse portion, we can choose wet sieving with or without dispersant. For the fine portion, we have sedimentation methods using a pipette or hydrometer. Combining the results from these two portions would give us a complete PSD curve. You can see that a PSD test can be carried out with or without dispersant. So, what exactly is a dispersant? It is a chemical agent used to separate the naturally cemented or aggregated soil particles. It also prevents flocculation of the dispersed soil particles during sedimentation in the suspension. The dispersant is particularly useful for separating silty and clayey particles. That's why a dispersant is more commonly used in the sedimentation methods for fine-grained soils. A dispersant is not recommended to be used when the soil is used as an engineering fill, a granular filter, and in filter design. Let's now see how the different tests are carried out. The mechanical sieving test is used to determine the particle size distribution of the coarse portion of a soil. The minimum sample size for the test is shown here. In this test, the soil sample is allowed to pass through a set of sieves with different aperture sizes down to 63 microns. The sieves are arranged in order from the largest aperture size to the smallest, with a collection pan at the bottom to collect the retained particles. The sieves retain particles of specific sizes, allowing for the classification and quantification of gravel, sand, and other coarse particles present in the soil. At the beginning of the test, individual particles larger than 20 mm are separated using a 20 mm sieve. We then sieve the fraction retained on the 20 mm test sieve using appropriate larger test sieves. The remaining soil, which is the soil portion passing 20 mm, is washed with clean water to remove particles smaller than 63 microns and oven dried. Then the dried soil is placed on the top sieve, and the sieves are mechanically shaken in a controlled manner. The shaking action causes the particles to be separated based on the size, with the larger particles retained on the upper sieves and the finer particles passing through to the lower sieves and collection pan. After sieving, the retained particles on each sieve are carefully collected and weighed. The PSD of the fine portion of the soil is obtained using the principle of sedimentation. We'll explain in more detail the sedimentation theory later. The key concept is to mix the soil with distilled water to create a suspension, followed by using either a hydrometer or a pipette to measure the settling behavior of individual soil particles in the suspension. In Hong Kong, the hydrometer method is routinely used by all laboratories. Hence, only the test procedures of this test method is briefly described in this video. Let us now briefly talk about the procedures of the test. We first carry out an assessment sieving to remove particles larger than 2 mm. A dispersing agent is added to the soil, and these are thoroughly mixed to create a suspension. The soil suspension is then put into a mechanical end-over-end shaker for 4 hours to achieve full dispersion of the soil particles. We then pass the suspension through a 63-micron sieve and transfer the suspension passing the sieve to a measuring cylinder. We allow the suspension to be placed in a constant temperature bath for at least 1 hour. After the conditioning period, we shake the suspension end over end manually. Then we put back the suspension to the constant temperature tank for the soil particles to settle. At specified time intervals during the settling process, we measure the density of the suspension by a hydrometer. These readings provide information on the settling behavior of the soil particles and allow the particle size distribution of the soil to be determined by the sedimentation theory. We take the last reading after a period of 24 hours. The sedimentation test basically measures the change in the soil suspension density with time. But have you ever thought of how and why it works? The sedimentation theory is based on the fact that larger particles suspended in a liquid would settle more quickly than smaller particles, assuming all the particles have similar densities and are spherical in shape. According to Stokes' law, the particle's terminal velocity is proportional to the square of the particle diameter. Therefore, the proportion of different-sized particles can be figured out by monitoring the liquid density with time. However, Stokes' law does have its limitations. Firstly, it only works well for soil particles larger than clay size, which is about 2 microns. This is because Brownian motion dominates when the soil particle size is too small. Hence, only the distribution of silt-sized particles can be obtained by the sedimentation method. Secondly, Stokes' law assumes a spherical particle shape. For clay particles which are platy-shaped, the sedimentation method tends to overestimate the proportion of fine-grained soil. The PSD curves obtained from a sieving test and a sedimentation test may not align or join up for the same soil. Can you guess why? Well, the test itself is actually based on 2 samples, one for the sedimentation method and another one for wet sieving. Additionally, there can be possible particle breakage during shaking. These factors are more pronounced in coarse-grained soils, resulting in larger gaps in the PSD curve. Geospec theory recognizes this discrepancy and provides a solution by using a modification factor X to create a continuous PSD curve. This method assumes that the distribution obtained from sieving is more accurate than from sedimentation. The modification factor X is obtained from the equation as shown here. You may notice that in this method, the percentage passing the 63-micron sieve obtained from wet sieving is used as a reference value. Once we have calculated the factor X, all sedimentation test results are multiplied by this factor. Then, the gap between sieving and the sedimentation test results can be bridged to create a continuous PSD curve. We've talked about some basics in the test methods, the theory behind, and also the interpretation. So, what are the possible applications of a PSD curve in practice? One major application is soil classification, from which we can categorize soil based on their properties and characteristics. By analyzing the PSD curve, we gain valuable insights into the soil's composition and its behavior in terms of compressibility, shear strength, compaction, and permeability. It allows geotechnical engineers and engineering geologists to predict the soil behavior under various situations, such as in excavation and foundation design, and in slope stability analysis. There are often contractually binding material specifications that put requirements on the PSD. For example, the HKSAR government's General Specification for Civil Engineering Works contains the requirements on PSD for different types of fill materials as shown in this table. Another application of the PSD curve is the filter designs for a geotechnical structure, for example, behind a retaining wall. You may refer to GEO publication number 1/93 for details. Some soil parameters may be estimated using information from the PSD curve. For example, the coefficient of uniformity of a soil as shown here. The coefficient of permeability of a sand can be estimated from Hazen's formula. In unsaturated soils, the soil water characteristic curve SWCC may be modeled from the known PSD curve. We hope you have gained valuable insights on the theories, procedures, and applications of these tests. Join us in the next video as we explore another exciting topic in soil testing. Thank you for watching.